Hello, welcome to lesson 3 of my USA Biology Olympiad course. This lesson is about water. So, you might have heard many times that water is basically like the sign of life on outside planets, which I will talk about later in this video. But basically, as you can tell, that water is very important to life. Literally, all life on Earth needs it. And so, it's, justified that a whole lesson will be dedicated to about water. So basically, um, this lesson is going to be actually pretty short. There's only three concepts to it, but there's a lot of information packed into it. So you're definitely going to see a lot of the chemistry information from the past lesson playing into this. So I would say if you don't know anything from the last lesson, you should go review it. But um, yeah, this lesson's not really in depth, but very has a lot of quantity to it. And so yeah, just listen up. So basically, the first main important concept I need to understand about water is that water is polar. So I know I talked about this on the last lesson, but basically, polarity is just the uneven charge of a molecule. So water is really polar because we know that one side is the hydrogen. No, yeah, one side is the hydrogen atoms, and then the other side is the really big oxygen atom. So as you can see here, the hydrogen atoms clump together on one side because this side is all negative and this side's all positive because of the uneven charges. And so, um, basically, water is a really polar molecule, and that gives it all of its special properties. So, uh, oxygen is more electronegative than hydrogen, so the electrons of the covalent bonds spend more time closer to the oxygen than to the hydrogen. These are polar covalent bonds, here as it says here. And then this unequal sharing of electrons in water's V-like shape make it a polar molecule, meaning that its overall charge is unevenly distributed. So yeah, that's basically all you need to know for this first concept. Just really try and understand polarity. I know when I first started learning about polarity, I didn't really understand it that much. Just think on it. Yeah. Okay. So as you can see, 3.2 is a really hefty concept. So basically, these are just all of the properties of water that make it really important to life. So for one thing, there's cohesion and adhesion, and from that, surface tension. So once again, you'll find that most of these properties all emerge from, actually, probably all of them all emerge from the hydrogen bonds and the polarity. So basically, cohesion is the phenomenon for hydrogen bonds to hold on to um, like the substance together. So basically, cohesion is the ability for water to stick to itself. So like you might notice that like if you drop like a drop of water, the water isn't just gonna like flatten out immediately. It stays like a bubble together. That's probably because of the cohesion of it. Like it's sticking together. The water sticks to itself. Um, and basically, one result of cohesion is surface tension. Um, I'm pretty sure we all know what surface tension and like surface tension is. Like, if you have like a glass of water that's really full, then you start dropping water into it, you'll see that it actually goes above the rim, but it like sticks together, like at the top of it. It's like kind of like a dome, like a really short dome, because that's the surface tension of it. This cohesion is keeping the water molecules together, and so yeah, that forms surface tension. So similarly, there's also the concept of adhesion, which is water's tendency to stick onto other things. Um, the only exception to this is the hydrophobic molecules, which are literally just like water can't stick onto it. But yeah, you'll notice that water sticks onto basically like anything you pour it on, except hydrophobic things, which I mean we see every day. Water's everywhere. Okay, this next segment's kind of a bit hard to understand conceptually. So just like we all have like these ideas about what heat and kinetic energy and thermal energy are, just like throw those out the window for right now. Like, no, these definitions are gonna get kind of wonky. So anything that moves has kinetic energy. So kinetic energy is the energy of motion, and then the kinetic energy associated with the random movement of atoms or molecules is called thermal energy. So thermal energy is related to temperature, but they are not the same thing. So temperature represents the average kinetic energy of the molecules in a body of matter, regardless of volume. And then thermal energy of a body reflects the total kinetic energy, thus depends on the matter's volume. So like thermal is like total kinetic energy, temperature is average kinetic energy. So obviously you can see why thermal energy relies on volume more, because the more volume, there's going to be more total. So yeah. And then so we all know this concept of thermal energy where like, it's looking for equilibrium. So you feel like if you have like a really cold thing and a really hot thing, the hot energy, like the heat, the thermal energy will transfer into the other object, the colder object, and so it evens out eventually. And so basically, The transfer of energy from thermal energy transfer from one body to another is defined as heat. So yeah. And then there's a really nice measure of heat that's called a calorie. So a calorie. So calories are not, just the things that you eat and make you fat. I'm sorry, I'm just kidding. Nobody's fat. Um, a calorie is the amount of heat that it takes to raise the temperature of 1 gram of water by 1 degree Celsius. So a calorie um, is also the amount of heat that 1 gram of water releases when it cools by 1 degree Celsius. So, and then as you can probably tell, kilocalories is that times 1,000. So like 1,000 calories is the quantity of heat required to make the temperature of 1 kilogram of water by 1 Celsius. So, by the way, the calories that they say on food packages are actually kilocalories. So, yeah, that's because there's not really that much energy like that. Because the human body needs a ton of energy, so you need to eat a lot of energy, right? So yeah. But yeah, that's going to be a unit that's recurring a bit. Just try and understand a bit, but you don't need to know the whole definition. So the next property of water is specific heat. So specific heat is the amount of heat that is absorbed or lost for 1 gram of that substance to change its temperature by 1 Celsius. So obviously, the specific heat of water is 1 calorie per gram. Because like I just said, a calorie is like the amount of one, yeah, that's what I just said, yeah. But basically, specific heat is just the amount of heat that something needs to warm up. So water has a really unusually high specific heat because of the hydrogen bonds, and so because the specific heat is really high, that actually makes it really suitable for life. For example, that's why our oceans aren't like baking all life in the ocean because the ocean just isn't cooling up that much. Like for example, like it can sit in the sun all day, but only changes temperature by like a few degrees while still absorbing a ton of energy, which is a really nice thing that keeps us alive. And so, another thing that water has is heat of vaporization, a really high heat of vaporization. So basically, the heat of vaporization is the quantity of heat that a liquid must absorb for 1 gram of it to be evaporated. So basically, water has a pretty high heat of vaporization. That's why water isn't readily evaporating. I mean, it is readily evaporating, but that's why water isn't, just evaporating away like every single day. So that's what I just said. What I just said earlier. Basically, a really fun fact is that water is constantly evaporating. Like as long as it has like a place to go, like as long as it's not like a closed system, water will always evaporate, and it's always evaporating at the surface too. And so if you look really down, really low at like a microscopic level, you'll see that like the water molecules are actively turning into gas, but it's such a small amount that it's not noticeable. Like you can't like just look at it, but if you do leave a glass of water like outside, like not outside, but like just anywhere long enough, it's gonna disappear. So that's really cool. And then so because of the high heat of vaporization, there's also a similar concept about water's evaporative cooling. So this is basically why most animals sweat because basically evaporative cooling occurs because the hottest molecules, um, those with the greatest kinetic energy, are typically the ones who evaporate and turn into gas. So like if you sweat, like all the heat is gonna just evaporate away from you. So that's why sweating is really nice because it keeps you cool. And so most animals, like we humans, need sweat, or else we would dehydrate, or like we would bake really easily. So yeah. Now another concept that's really cool is the fact that ice floats. So ice is less dense than water. And the reason for this is because when water freezes, like it forms like the ice forms a crystalline structure that's less dense than water. It expands outward, and the molecular structure expands. So that's why ice is less dense than water. And this is important biologically because that's why we have floating icebergs. That's why habitats like Antarctica and the Arctic exist because the ice isn't sinking to the bottom of the ocean, it's staying up. And it's really cool because like if ice expands and then it sinks, then the water levels will be rising like crazy. So yeah. Um, so there's also this really nice concept I need to understand is that water is the universal solvent. So basically, water will kind of like dissolve anything that it touches. Kind of. I mean, not like in the way that like hydrochloric acid like just like will turn you into nothing, but like water will, because of the hydrogen, because of the polarity, because of the hydrogen bonding, it will actively tear apart your molecules when it comes in contact with you. And so yeah, here's some definitions I need to know. So a liquid that is completely homogeneous, it's a mixture of two or more substances, is called a solution. And so the solvent is the thing that dissolves the like the thing that's being dissolved, and then the thing that's being dissolved is a solute. So like for example, if you put salt inside water and then the salt dissolves, the salt is the solute, the water is the solvent, and then the salt water mixture is the solution. So water is the solvent of life. Just know that. And then an aqueous solution is one in which the solute is dissolved in the water. So salt water is an aqueous solution. Um, 10%, I forgot what it's called, a 10% iodine solution or something. I don't know. But like when you dissolve lye, also known as NaCl, or not, sorry, NaOH into water, that's also an aqueous solution. And basically, whenever you dissolve something, like the ions of the dissolved material will, be covered in like water molecules. It will be like wrapped around it. And that wrapping of molecules around the ion atom or the ions is called a hydration cell. So here's one fun thing that I learned from chemistry that this book doesn't really talk about. So this is extra information that I'm providing to you. So typically you'll see that polar things dissolve other polar things. And so and you'll find that non-polar things dissolve non-polar things. And so like non-polar things and polar things don't really dissolve each other. Of course, there are always exceptions to this, but that's like the basic general rule for it. And then the term miscible is like there's also a term called miscible, and that means that like a solution like solutions are miscible if you're able to mix them together and like dissolve them into each other. So polar and polar are miscible, non-polar and polar are miscible, but polar and non-polar are immiscible, which means that they can't be mixed together. So like, that's like oil and water. So water is polar, oil is non-polar. So they're immiscible. You can notice that when you try mixing them together, the oil is going to float on top because they're different densities. So yeah. Okay. And then there's also hydrophobic and hydrophilic. I kind of talked about it earlier, but basically hydrophobic, just use your Greek like prefixes. Hydrophobic means that something is like not like it's avoidant of water. It's not going to stick to water. It's like going to repel water. And a hydrophilic is basically something is attracted to water or it sticks to water. And so, just that's like a basic general thing, but it's important in biology because I know it right now because I'm doing protein structure for my research, but basically, you'll find that in protein structure, like a lot of the ways that proteins fold is basically based on hydrophobic and hydrophilic reactions. So, the reason that like proteins fold in like the specific way where like they're like clumping together like a piece of hair is because um, all over the protein backbone, there are hydrophobic and hydrophilic structures. And so, there's water all inside the cell. There's literally water all over inside of you. And so, like water plays a really big role in how protein relations work. And so the hydrophobic, like ions or like the hydrophobic like parts will, fold inward and face each other, while the hydrophobic parts, no, yeah, the hydrophilic parts face outward so that they can like interact with the water on the outside, and the hydrophobic parts won't interact with the water on the outside and won't interfere in things. So yeah, it's like a fun fact to keep in mind. And then, okay, this part I don't really understand it myself, but so you don't need to know it that much. Basically, all you need to know is that like about solute concentrations. So in a solute, there's obviously concentrations of things. Like I said earlier, there's like a solution where it's like 10% of NaOH, and then there's water. And so you dissolve the NaOH in water. So that's like the concentration of it. 10% of that of NaOH and 10% of water. No, and 90% of water. So, I'm sure you guys have all heard about moles or Avogadro's number. You guys need to like it should be known. So like this is basically like the universal like I mean you're gonna see it everywhere. It's like just it's the big number of chemistry. So it's 6.022 to the 10 to the 23rd power. So that is 1 mole. And so 1 mole can be 1 mole of anything. It can be a mole of a molecule, 1 mole of molecules, 1 mole of atoms, 1 mole of like particles, just 1 mole of anything. And so it's like I don't know where he got this number from. He may have just like made it up on the spot, but like basically like this is a number we used to like just like like just for anything like molecular. So like the mass that you see on the periodic table is the mass of 1 mole of that atom. Like if we ever like if we ever like look at like chemical reactions, the things that we're calculating with is 1 mole of that atom or 2 moles of that atom, etc. And so like 2 And so, yeah, just remember 6.02 to the 10 to the 23rd power times 10 to the 23rd power. Yeah. And so, molecular mass is just like, it's the sum of all the, like I said it before. Yeah, it's the sum of all the masses in a of the atom in a, sorry, the sum of all the masses of all the atoms in a molecule. It's just the mass of a molecule. Yeah. And then there's also a thing called molarity. So basically, the molarity is the number of moles of a solute per liter of solution. So like, if there's like 10%, like I said, I used the example before, 10% NaOH, 90% water in that NaOH water solution. So like there would be one NaOH for every 9 water molecules. So yeah. And then lastly, this is what I was talking about in the beginning of the video, but water is a sign of life. If water exists, then life is likely to develop as well. That's how we came about. It's because basically the main theory is that asteroids landed on the Earth and they're carrying water molecules, and then they filled the Earth with water, and then that's how life began to form. And so basically, water is a sign of life, because if we look on exoplanets outward, then if we see water on the planet, then there's a good chance that there's also life associated with it. And that's why scientists believe that there's life on Mars, or there used to be life on Mars back when the ice wasn't frozen. And also they believe that there's life on under the ice of Europa, which is one of Jupiter's moons, because there's a really there's life, there's like water there. And so that's why like everywhere there's water, there's a high suspect that there's life there, because water is, it's the element of, like, not the element, it's the molecule of life. We need it. So yeah. Okay, lastly, this part is pretty short. I'll keep it like simple. So basically, we talked about before about like equilibrium in chemical reactions, where just like like reactions are reversible, etc. So yeah, this will come into play here. So basically, an acid is a substance that increases the hydrogen ion concentration of a solution. So some really well-known acids include hydrochloric acid, HCl, sulfuric acid, which is HSO4. Those are acids. I think we all imagine acids to be like burning the skin or something like that. But basically, the actual definition of an acid is it increases the hydrogen ion concentration. So like, for example, HCl will turn into H plus, and then Cl minus. So you can see H plus. It increases the hydrogen ions, and then the source of the H results in an acidic solution. So yeah. And then a substance that reduces the hydrogen ion concentration of a solution is called a base. So a base, for example, a really well-known one is ammonia, NH3. So NH3 plus, NH3 can bond with H plus and form ammonium, so NH4. So like you can see that like bases, they take in hydrogen ions, acids release hydrogen ions, and you can kind of assume that they cancel each other out, and they do. So basically, like, this is important to water because like where they dissociate into their hydrogen ions is usually in water. So like I've been using this example a lot, but NaOH and water, NaOH in water dissociates into the ions of Na and then OH minus, and so this base, it reduces the H plus concentration. So so OH, so typically when you look at molecular formulas, you know that OH is typically a sign of a base, and then H plus is typically a sign of an acid, because OH is like the opposite of each kind of, you can think of it like that. So wait, and either like the base reduces the H plus concentration. So solutions with a higher concentration of OH minus than H plus are known as basic solutions. A solution in which the H plus and the OH concentrations are equal is said to be neutral. And then, as you can probably assume, the ones where H plus is more prevalent is acids. So basically, okay, yeah. There's also the pH scale. So the pH scale is basically just a way of like measuring, the acid base level. As you can see in this photo here, the lower the pH number, the more acidic the solution is, and then the higher the number, the more alkaline or basic the solution is. So yeah, wait, that actually makes sense, because we know that NaOH is a base, and then NaOH is also known as Li, or alkaline. So yeah, really cool. So basically, the way that pH is calculated is that like let me see. So wait, hold on, I need to reread how to like explain this. It's like some weird things. Okay, yeah. So the pH, you basically have to use like, okay, yeah. In any aqueous solution at 25 degrees Celsius, the product of the H plus and the OH minus concentrations is constant at 10 to the negative 14th power. So basically, um, so as in a neutral solution of 25 Celsius, H plus is 10 to the negative 7th power and OH is 10 to the negative 7th power. So basically, you can calculate pH by taking the log of the amount of H's. So basically, in a neutral solution, if you log 10 to the if you log 10 to the negative 7th power, you get 7. I'm telling you get negative 7, but yeah, 7th. And so, oh yeah, you take the negative log, so it cancels out. So yeah, you get 7. So it's, in a neutral, the pH is 7. Well, would you look at that? The neutral pH is 7. So yeah, you can calculate like this, okay? So like, let me see, like, oh yeah, also don't forget to realize that like since the numbers are negative, the bigger the number, the less the H concentration is. So keep that in mind. So like in a really basic solution, the H concentration is 10 to the negative 14th power. So that's 1 over 10 to the 14th. So that's really small. And so if you negative log that, you get 14. So that's a really low concentration of H ions, and so it's very basic. So it's alkaline. And then, yeah, that's how you calculate it. I don't really think calculating pH is really important. Just know how it's calculated. You just use log and then 10 to the power, stuff like that. I remember when I first learned about this, I was so confused because I forgot that like negative exponents get smaller as they get bigger. So like, yeah, but yeah, just don't forget about that. So yeah. All right. And then there's also a thing called pH buffers. So basically, a buffer is a substance that minimizes changes in concentrations of H plus and OH minus in a solution. So basically, it just like, like reduces like the potency of acids and bases. So like for example, a really well-known buffer is H2CO3. So this is actually carbonic acid, which is like the stuff in soda. So basically, carbonic acid it reacts to like rises in pH and drops in pH. So like so the reaction for it is reversible, which is a really common thing in buffers. So basically, when the pH rises, so that means that it gets more basic, H2CO3 will dissociate into HCO3 and H plus, the ions. So basically, it releases ions when it gets more basic, so it goes back to neutral. And then when the pH drops again, the HCO3 and the H plus bond back together into H2CO3. So it's a reversible reaction. And then, excuse me, sorry. So yeah, just know that buffers like keep things together. So I mean, it's because of like the chemical equilibrium, reversible reactions. That's how buffers work, just like back and forth. Okay, last but not least, ocean acidification. So basically, there's a lot of chemical reactions that happen in the world right now, and then one of the main ones is ocean acidification. So this is where oceans are getting more and more acidic because of the release of the burning of fossil fuels, the CO2 in the atmosphere, greenhouse gases, etc. And so the ocean pH is becoming lower and lower every year. And so while it is a really slow rate, once it gets to a certain point, then life will be basically impossible to happen at a certain pH level. And so while it's not super acidic, we still want the ocean to be around 7. And right now it's probably at I don't know what it's at. But yeah, it will drop 0.3 to 0.5 pH units by the next century. And so that's really that's a lot. 4 of those would reach the level of hydrochloric acid, which is enough to burn your skin off. So it's really important to keep keep watch of this greenhouse gas emissions, stuff like that, to prevent ocean acidification. But yeah. Okay. All right, that is the end of the lesson. Like I said, a pretty short lesson, a lot of information to keep track of. Just keep on studying. Okay, not bad.